Hello everyone. Thank you for joining for my presentation. Today I'm talking about a case study for the storage isolation to avoid the system slowdown propagating from other containers. So this slide shows my introduction. So my name is Naoto Yamaguchi from AGL Corporation. So this slide shows today's outline. So at first, I'm talking about the background for our work. It's including the AGL ICG activity. So next one is the main content. So case study for the storage isolations. And finally, it concludes my presentation. This work is a part of AGL Instrument Cluster Expert Group. This expert group motivation is create a best platform for instrument cluster with IVI and other Linux systems. So there are different system requirements between IVI and cluster and others. This platform is built from open source technology. It needed to independent from existing proprietary software component. And it needs to be able to choose open source software component or proprietary software component. It's our motivation. Generic system design of AGL ICG. So, instrument cluster and IVI into one system. Instrument cluster is a required functional safety. Connecting to one or more displays. Connecting to speakers. Connecting to phone by Bluetooth, USB, and Wi-Fi. Connecting to USB devices. Connecting to on-board, off-board sensor devices by I2C, UART, and SPI, and etc. Connecting to other in-vehicle ECU by CAN, Ethernet, and etc. What are the product development issues? That answer is quality and robustness. Instrument cluster required to the functional safety SLP because instrument cluster has telltale functions. Telltale show critical failure information to driver. Quality management is there have separate quality requirement between instrument cluster and RBI. It's issues. So approach for functional safety and etc. So make main function and safety function isolated by isolation method. So our strategy is a safety island approach, but its design is dependent on your systems. ICG main focus to the main function part. This slide shows a path between IVI and the instrument cluster. IVI and similar other Linux systems require to the rapid innovations. On the other hand, instrument cluster and similar other Linux systems require to the advanced quality management. It's a first puzzles. IVI and other similar systems require to various functions. On the other hand, instrument cluster and similar other systems require to the selected functions to avoid including the many bugs. It's a second puzzles. Our answer to the puzzle issue is one more isolation method. That means add one more layer on low-level isolation layer to isolate the functions. This one. So our approach is isolated each software using the Linux container technology. We call this architecture is QM isolation. Why use Linux container? It's an operating system level virtualization method. It running multiple isolation Linux systems containers on host using single Linux kernels. It realized to isolate root file systems on Linux kernel by using change root. Control resource such as CPU and memory by using C groups. And hide resources from other containers by using namespaces. So Linux container realized to key feature for QM isolations. More detail of the technical concept, please check this my presentation. Technical detail for QM isolation. So today's topic focus to the software stack isolation. So Wings Sync should separate root file system between instrument cluster and IVI. Because instrument cluster are built by high-quality assurance software and will not change after SOP without critical bug fixes. On the other hand, IVI side are built by standard software and will change after SOP to upgrade functions. So Linux container also realized root file system isolation. Software stack isolation is realized by fully separated root file system. It realized to the all software binary is separating each container. At this point, realizing it is possible to use another version of the software between containers. Easy to upgrade software binary. But antinomy is just shared library cannot share memory between containers. And it causes heavy storage access more than standalone systems. So the typical system design, the system has one storage devices. That is used program storage and read-write data storage. And that storage uses NAND flash memory device such as eMMC or UFS. Write performance is from half or a quarter of the read performance in typical NAND devices. What problem does it cause? When each container reads the program from the storage devices, that operation will slow down due to device access conflict. When each container writes data, that operation will slow down due to device access conflict. It's a problem. So next topic, the case study for storage isolation. But first, I'm talking about the overview of our proposal. This proposal, base design of the log disk-based solution, was proposed at the AGL AMM 2024 Berlin. It aimed to avoid system slowdown propagating from other containers. We proposed to combination use between PHRAM block device and the ERFS file system. It realized to transparent memory saving and the good performance and intercontainer root file system isolation. On the other hand, last proposal is not including a verification feature. That means the root file system verification is required in current typical device. In this session, we propose to updated ROM disk solution with verification features. At first, a recap for proposed ROM disk solution. How to resolve to this issue? The easiest way is the storage separation between cluster and others. This. On the other hand, it requires 2 or more storage devices in the systems. On the other hand, it causes an increase in cost from a single storage design. The proposal design as shown. The storage for the cluster uses ROM disk. It is possible to keep a single storage design. It is possible to avoid slowdown propagation from storage access from the other containers. This one to this one. It's separated. The role of host root file system is managing and bridging between containers. We think so. Better solution is using ROM disk. The detail of proposed design. It is use MTD PHRAM block device and ERFS file systems. That's strong point. Both component possible to use after Linux kernel since 5.4. That means do not need extra kernel patch. MTD PHRAM device support one or more disk, but not support partition. Possible to use in 2 or more root file systems. ER supports compressed and non-compressed data block. It is possible to reduce total RAM usage if it uses a compression mode. Our reference design. It developed using Arca H3 starter kit and a Kingfisher board with yoked downwell release. It did not require to custom patch other than backboard. It required to configuration only. That backboard is a U-boot ERFS support available after 2022-07 release. Arca BSP used 2020.10. It needed a backboard. Cached PHRAM support available after Linux kernel 5.19. This point need to backboard. Changing point from the pure BSP. Task 1. ROM disk images load to RAM before Linux kernel booting. Add 2 disk image load operation in U-boot. Add PHRAM disk information to the kernel command line. Add reserved memory area to use ROM disk DTB. Add a second ROM disk mount operation in user. Second task is a ROM disk image installed to eMMC. The install kernel image, DTB, and 2 ROM disk images to an eMMC partition. The uncompressed ERFS file system image was written to MMC block 0P1. That image includes kernel image with DTB and compressed host and cluster ERFS images. U-boot copies this file to memory from MMC block 0P1 using ERFS load command. This one, and this operation. The DTB has two reserved memory area to use ROM disk. This one and this one. U-boot sets the mount parameter for the host root file at the kernel command line. When the Linux kernel boot with this parameter, PHRAM driver creates an MTD block device using the physical memory address and the size. This one and this one. Command line is this one. A user and service create a second PHRAM disk using the sysfs interface. When this parameter writes the PHRAM sysfs interface, this one, the PHRAM driver creates a new MTD block device using the physical memory address and the size. After that, we can mount a block device to root file system. That's all of the recap part. Next part is the improved design and evaluation. Improved point from 2024 Berlin design. The updated design includes how to verify the ROM disk image. We propose the two types of the strategy. Type 1 strategy is it's verified by U-boot before the Linux kernel boots. That design requirement is that verification data shall be created on integration time, and that the verification data creation shall be included in the Yocto build. Type 2 strategy is it's verified at the file access time after the Linux kernel boots. The design requirement is the same as type 1. And the common restriction. This reference design is out of scope for how to encrypt-decrypt verification data to realize a chain of trust, because that is highly dependent on your system design. That POC shall be developed using the Yocto course gap. First one, type 1 verification. Its ROM disk images are verified by U-boot. Our proposed solution is to create a new image recipe to create an outside disk images. At first, wait to operation completed to our inside image creation. This one, and waiting this one, and this one. Second point, install Linux kernel images and ROM disk images. This description, install kernel and DTB and host ERFS images. After that, create and install sh256 as from ROM disk images. This one, create the hash data file. Changing point from previous design. Add an encrypted hash file load to U-boot. If your system needs kernel verification, you can use a fit image-based verification feature. Decrypt the encrypted hash file to use ROM image verification. And calc ROM disk image hash and compare the calculated hash and the decrypted hash. It's a changing point. Next, type 2 verification. ROM disk verified at the file access time. This solution is DM-Verity integration uses meta security, and it provides integrity checking for block devices. It's a type 2 verification solution. At first, I share the overview of the DM-Verity. DM-Verity is an infrastructure for verifying the block devices. It verifies the data block using the hash that is calculated at a boot time. That per block hash is verified by the upper level hash. This one verified by this one. Each hash is verified by a higher layer hash. This one, and this one. The root hash, this one, is on top of the hash tree. The block verification runs at the access time only. When a file has been read into the page cache already, that verification does not run, because that timing does not cause the block device access. It's the overview of the DM-Verity. How to enable DM-Verity? The meta security layer enables some security feature in Yocto build. How to use DM-Verity using the meta security? It's described at the document inside the layer. Add meta security to VB layers conf and add some config to local config. This one. That basic method is using initramfs. On the other hand, the proposed ROM disk solution did not use initramfs. It's an issue. It requires an alternative method other than initramfs. Linux kernel supports DM-Verity configuration through the kernel command line. This point is described at this web page. Please show after this talk. And I name DM-Verity with config DM init in kernel config. This one. Meta security provides the DM-Verity image class. It adds the hash creation task to the predefined image recipe. DM-Verity image defines the target images. It uses this pine. DM-Verity image type defines the target file system type. It uses this time. When you build a target image, it creates and adds a verification hash to the target images at this path. It automatically creates a separate verification parameter file. In case of the proposal of disk solution, it creates an inside image. An outside disk image is created by the same approach as type 1. Create a new image recipe to create an outside disk image. First one, wait to operation completed for inside disk image creation. Created waiting this one and this one. It installed a long disk image into outside disk image as this description. And install a verification parameter file to the outside disk image. It's this description. A typical system requires encryption for the verification parameter. You need to add an encryption operation at this point. Changing point or boot. Add encrypted verification parameter file role to uboot. This point. If your system needs a kernel verification, you can use the fit image. Decrypt the encrypted verification parameter and add the invalidity parameter to kernel command line. It's a changing point of the boot. It has issue of command line. I refer to the timeshift approach, but timeshift proposed a boot time configuration method. Timeshift method uses a separate disk configuration between the root file system and the hash. It writes root file system to MMC block 0p1 and hash to MMC block 0p2 in example. What is the issue for our solution? PHLM can configure only one ROM disk using the kernel command line. It couldn't have a partition in the ROM disk. That means we cannot use the two partitions. Proposed solution requires the root file system and the hash into one disk. How to do? The kernel command line parameter for the invalidity has a hash offset. We use it. It's too easy. Partition settings are same, and the set hash offset. But one of the point. Do not forget to change root file system device from dev mtd block 0 to dev dm 0. Attention. Next topic is evaluation. Evaluation point is how does the read performance decrease if the invalidity is enabled. Comparison between first access and the second access. It aims to check which scene decreased reading performance. Second one is a comparison between compressed mode and non-compressed mode. It aims to which operation has more impact on speed between LZ4 decompression and the SH256 hash calculation. Third point is a comparison between ROM disk and the eMMC. It aims to help with your choice of which solution to use. The restriction to test environment. It uses Linux kernel 5.10.x, which is the latest kernel version of the archives restarter kit. It added all the patches in the last AMM presentation. Evaluation summary. As an evaluation 1 shows, the ROM disk solution has a big read speed gap between first time of the file access and the second time of the file access. It is caused by the file system and the block device, not the liability. Additional point is that when you use the proposed ROM disk solution, it should not use non-scheduling at the block scheduler to reduce the overhead of the block devices. About 15% benefit as a result of this evaluation. As an evaluation 2 shows, in case of the ROM disk, data compression caused about 15% performance decrease. It shows that the decompression caused a bigger effect than SHA hash verification. Additional point is that we need to consider a trade-off between read performance and memory usage. As an evaluation 3 shows, the ROM disk performance is a specific result of the ROM disk solution. It shows that the bottleneck is a EMC read access. In this case, the data compression provides a benefit for read performance more than the decompression overhead. That means, data compress causes overhead in ROM disk solution, but the data compression gets a benefit in EMC case. Conclusion. AGL ICEG shared a case study for the storage isolation method using the ROM disk. ICEG proposed the PHRAM ERFS combination solution. This solution can be integrated using the fully open source solution. In this session, we proposed an extension to the last ROM disk solution. That is an added verification features. This solution realized to avoid slowdown propagating from other containers in the critical container. Future work. AGL Slowdown platform has the same issue between VMs. We'll investigate how to realize this solution in Slowdown platform. That's all. Thank you.